are live, I guess. So hello everyone. For those of you who just joined in, today we are going to continue on the comment programming language. So we started work last week by implementing a lexer for the basic grammar or the basic language declaration or definition that we did. And today we are going to start trying to parse the language and build up the basic infrastructure for the language. So we'll wait for 2 or 3 minutes so that people can join in, and we'll start from there. If people can hear me, please just leave a message in chat so I know that you can hear me well. If you can hear me, just write it out in chat so I can know people are actually hearing my voice. I'm not actually muted. Worth mentioning that last time I added some stuff to the GitHub repo. So I added a simple GitHub action so that when pushing or when creating pull requests, we kind of basically just checks that the build actually passes. So we don't merge passing builds. Or if people want to contribute, they don't accidentally break the build. And I added a little protection rule against master so that I don't forget and push directly to master. So I'll suppose that you can hear me and I'll just start. Alright. So as I said before, last time we created a lexer implementation for the toy language. So the grammar is defined in this comment G4 file and some kind of data format, and we identified what are the tokens that make our language, and we created a nice little structure that kind of creates or parses the tokens and returns them as an array. So in today's stream, we'll start making the infrastructure for the parser, and also we will be starting to look into making parsing math expressions, because they are, in my opinion, one of the most interesting parts. And if time allows it, we will go into parsing some basic statements that we have in the parser. So yeah, I guess without further ado, let's start. So the basic idea is I want to create after parsing, the next step is to do to create an AST from the tokens, and an AST is nothing but a data structure that represents the tree, a tree that represents your operations, your declarations, your variables. and their operations in general. And when we want to evaluate the actual program, all we have to do is like keep track of the data and walk the tree from in that first order, and that will supposedly like evaluate the tree. So to create the AST, we will need to define like some basic nodes. Every tree has some kind of nodes, and we will try from the top and create what we call a root node, and then we'll create basic nodes that makes like our integers, our numbers, our strings, or whatever, and then we will build up like from them other kind of expressions, other nodes that represents like some more complex operations like additional, multiplication, call to a function, getting like the index of some array, etc. And to do that, I would like to start with the new directory, and then I'll call it the parser. And the parser will have the file that contains the nodes declaration. And we know that every one of our types will have some kind of node, so it's better to identify this abstract structure that represents the node. And let's say that every node has some kind of value, literal value. So let's just call it a literal. Or yeah, so let's just call it a literal. Be a good idea. I can never spell literal. And every node is in the construct of the language is either an expression or a statement. The difference always between an expression and a statement, for those of you who don't know, is expressions cannot be used as the right part of an assignment. An expression can be assigned to some kind of variable. So in this case, we can always create like the two major parts that are an expression and a statement. And an expression and a statement are also nodes, so presumably they should like all implement the same structure. And we know that the tree that will represent our AST will start somewhere, and to identify the node that is going to mark the start of the tree, we are going to mark that node as a special node. We'll call it a root node. And this root node, as we saw before, like in the README, and the language declaration, it's kind of statement driven. So we have like a bunch of statements, and these statements kind of get evaluated. So to do that, we will a root node will have like some form of statements. How do you spell statement? Okay. So a root node will have a bunch of statements, and every one of these statements is gonna contain other statements and probably expressions and etc. etc. And these are the things that are going to make our AST. And so now I want to create the parser. So the parser is a struct, and it should have some kind of reference to something, but I won't care about that right now. I will only define the basic skeleton for it. So a parser should have some format, some method. And let's call it parse. And this parse call will return some form of root node. We'll know that's calling we know that calling parse will result in calling a root node and creating a root node, and that's cool. And we know that the parser will contain like from what we saw earlier, we'll see like it should have like some kind of lexer, and it should have a reference to the current token, to the token, and the next token, because we are going to make a parser that only needs one. At least I think I only need one look ahead instruction. I guess they are called some in language theory they are called LR1 or LL1. I don't remember. Yeah, we'll probably need other stuff, but I don't really know for the current time. I only kind of see like we need a current token, a next token, and probably the lexer to give us the actual tokens. And so what we should do is like to provide some kind of instruction to create the parser from a given token stream, and this will give us a parser. And yeah, so to create a parser, we'll know that we'll need a lexer dot a new lexer from the source, and we will create the parser. So the parser would be a parser lexer, and we'll probably need other types of initialization. Probably we'll do just init and then return the parser. We should initialize, so the init method should probably, so why are you complaining? Oh yeah, that's my bad. So we should initialize the first parser. So we need to initialize the current token and the next token, and we want to do that by identifying like two methods on the parser. We want to have a next lexer.token, probably current. How current we have it. Since we're not changing state, I suppose we do like just advance, same as we did for the lexer. And probably, well, if we need peak, we'll do it. Advance will basically so what should we put in advance? Should initialize the current. So advance will move the next token up to the current token and move and read the next token from the lexer. So supposedly this should do something like this. So we should make p.current token equals p.next token, and p.next token should equal to lexer.next, I guess. p.lexer.next, and next itself can probably return some kind of, I don't remember if we return something other than, so if it's 0 we just return end of file. Okay. Cool. And now we need to call p.advance the first time, and I guess we should add another time, the second time. So the first one will fill the next token, and current token should be null, and calling p.advance the second time will make the current token equal to the next token, and the next token equals to a new token. And with that, we suppose it's initialized. If we needed like anything else from here, any other type of initialization will go back. Go back there. So yeah, so let's go back to our nodes, because those are the ones that make the structure. So an expression, so to mark them kind of differently, an expression should have like an expression method that actually does nothing for now. And a statement should have a statement method. But it all right. It should have a statement method, and this is like some kind of a marker method, just to mark, because the type system of Go doesn't like doesn't support, but doesn't enable hierarchy very well. So if this was like some other language like C# or Java, it would have been like a little bit better. But yeah, we're using Go, so we'll go with the current structures. So the first thing to do is like a root node is a special type of node. So we'll need to implement node for it. And the literal in this case, I'm gonna return something that is empty for now. I'll go back. Maybe I'll go back to it later. And in our case, we have expressions and statements, and we will have some kind of we'll have like we want to, so let's do it this way. Let's start by writing the test for this. Okay, so let's do a parser test. That would be like easier to do, because I don't know actually how to do this yet. So let's create a test parser parse. The structure of the test should change, I guess, because it's actually asserting on a hierarchical data structure is going to be like trickier than expected. I'm very sure of this, but we'll do something nice to kind of enable us to test a little bit more easier. So let's see that we want to parse this. Let's say we are wanting to parse 1 plus 2, and so let's start smaller. Let's start. We want to parse 1. Let's create a new parser from the source. And when we call parse, we'll have a root node, and we want to assert t and root node, and we want to assert that equal, well, at least len, I guess, root node, I guess 1 root node dot statements. How is it flipped? We want to have at least one we want to have exactly one statement or expression. And yeah, so so if we take the root node and statements of 0 and we cast it to something like an expression, a number expression, a number literal expression, we want to have want to make sure that this exists. So I'm going to create the type struct. Make it into the node structure. So it's complainer for some reason. Yeah, it doesn't implement statement. Yeah, and we probably want to do this. For simplicity, we want to make expressions as statements. So let's implement expression for this. So let's call it, all right, works fine. All right. Okay, so now number literal does not implement statement, but it does. Oh, it doesn't. Well, all right. I want to search true, but it actually can convert it. I want to get the expression and take the actual value and want it to be 1. And of course I have to create a field. Type, let's say we support int. Let's make it simpler and say we support ints. Alright. Good. I guess this looks like a starting point. We want to be able to parse a single number as a statement. Of course, running this will fail because our root node is actually null. So let's try to make it pass somehow. Okay, so we start at parse. Oh, how about not returning? Return some kind of root node. That will at least make it not null. And the statement should have at least 1 item. So probably should have like at least 1. Yeah, but now we have, it should be able to cast, and it can't. So we probably should make the statements in here. And yeah. Alright, and before that we should like make statements of 0, something of a number, literal expression, right? And probably this will make it, yeah, so the actual value here is the 0 value for 1, so I'll make the actual value actually be 1, and this probably will make our test pass. Yeah, our test pass. So let's add another one. For now, I will refactor the tests later. Single number expression. So now, how about 2 number expressions? if I do 2, suppose that this is my source, I want this is 2, and I want to do for I, let's do for I, we want statement of I minus 1 to be equal to this, and the value to be equal to actually I. And our test will fail in this case because we only return 1. Oh, you see where I'm going with this. So this is gonna get a little bit hairier. So if I make it like, I make it this size too, well, it won't be able to test it because I only set the first and I can set the second. But yeah, I guess I can like do this and make the actual value of 2, and that'll work. But we somehow will need like something more better than this. And so let's parse our first operator expression. So addition expression. Well, instead of having that, we will want to have this, and we want to have one statement, and we want the first statement to be an addition. Let's do an add expression. And let's say we want this to be able, and we want one. Oh, not that. So we want the expression that left of it, because an added expression is kind of a binary expression, and we want the left side to be something and the right side to be another thing. So let's say can equals root node. We only want to know if it cans, and we want the expression dot left to be a number literal expression. And in that case, we want to also be able to do it, and we want to be able to have the actual value. So yeah. So the left one a 1 and the expression that's actual value. And I want to do the same for the right part. And the right part wants it to be equal to 2. So this now doesn't compile. Let's go to nodes and add the expression, construct that it has some kind of expressions. So let's implement expression, and let's call it E. And we won't care about the literal for now, the statements and the expression. All we will need to have is a left, which is an expression, On the right, choose an expression. And for now, that's it. Expression. I can't type today for some reason. Okay. And again, we know this won't work. Undefined I. Yeah, sure. It will return one item. And at this point, I guess we will need to make a better parsing implementation. So what I would like to have is before actually parsing the nodes, I want to start with something simple, easy. And I want to like loop until so as long as we don't reach the end of the file, we're gonna keep trying to parse. So we're gonna do like statement equals p.parse statement. And if statement is not null, I'm gonna do statement equal, gonna append this to the list of statements. Right? And then we will return our statements. So how does it look like, our parse statement function? So this returns some kind of statement, and in our case we want to see like on a switch on the current token, and we would like to see what's the actual type, and based on that basically we'll try to identify. So the idea is like if we have a declaration such as var, starting a statement with var would mean that we have a declaration. Starting with an if would mean like we have some kind of conditional statement. Starting with a for would mean that we will have some kind of a loop construct. But anything other than that, because we have statements and then we have expressions, but anything other than that is actually an expression. So I will do like a default because I will need to add statements. But that's for later because we want to like make the groundwork for the expression parsing. So in this case, we will return, we'll actually try to parse an expression. So we'll return a p.parse expression. And how does a parse expression look like? Well, every expression looks so let's make this return an expression, and an expression is basically a statement. And in our case, we only now have an add expression, so we kind of take on the first token, and we say, so p.current token. So this is like the current, and we say I guess that is like stir convert, yeah, stir convert. Parsing, yep. So I want to parse an integer, which is the current dot value or literal, and we want to parse it in base 10 for now, and we want to say like we have a 30-bit integer, and the actual value is this, and probably this returns an error of some kind. Yeah, I think. Now we can create the left side. And we know that the left side is the number literal expression with the actual value as the actual value. We'll make it left value. And for now, so this returns what? Probably this doesn't return what I expected to return. Oh yeah, it returns a N64. It's probably better if we use an N64. Yeah, it doesn't matter for now. And we want to consume, so current.advance. So the parser.advance consume the current token, and we say expect p.advance expect token type for plus token. Yeah, we said like token dot plus add. I don't remember what it was. So we want to advance and expect, and advance and expect basically means it's like if current type is different than expected, expected that type. Oh. Hello, Zakaria. I don't know where we made our token types. Oh, yeah. So alright. So this should expect a token type. Yeah. So if both of them are different, a good idea would be to, not a good idea, we should panic because this is not what we expected. We should add proper error handling, but for now I'll just panic. And say expected something, got something else. So I expected the expected and got p.current token. Little. All right. Otherwise, I will advance. And this practically means consume the plus token. And then I'm gonna do the same thing again for the right part, which is and then I will return a add expression. Yeah. Yep, that looks about right. So this will actually parse the expression. And of course, this should advance too. But yeah, I guess eventually the whole code is gonna be like thrown out. for this, but yeah, this is like just for demonstration that we actually can succeed like by doing this. So let's try to run test. So expected something. Yeah, I should probably wrap it in and 64. I expected 2, but I get 1. Okay. I have some kind of bug. So we advance twice. Okay, so let's kind of debug it, although it defeats the purpose of this. So what's current in this case? So current is 1 for some reason. What's the input? Lexer has source, and why the current is 1? Are we advancing correctly? Okay. So let's search debug also this. Probably are not advancing correctly. Advancing the second time, and the first time we... No. The first time we call next, well, advanced, we are at parse expression and call in advance. Now the current is 1. So let's see our Lexer. Our Lexer's position is actually 0, 1, 2, 3, 4. Position of the Lexer is actually 5. So the current token is, or the next token is 2. But the current token is plus in here. So the current token now is 2. And the next token should be on the file. Yeah. Now the current token is 2. Alright. And the right value is 1. Well, that's surprising. What's current? Oh. Why do we have a reference to this? My bad. So yeah, let's try and repeat this. Yeah, so now the test passes, but as soon as we add something else, it's gonna break. So because this can be any type of expression and not necessarily an addition. And if we continue to have a reasoning that thinks that for every expression we should have a matching node, we wouldn't go like too far, because we would have to make a node for every type of binary expression, and which basically they kind of do the same thing. So let's sketch it out. So the idea is I want to have 1 and 2, and I want to have this as a number, and I want to have this also as a number, and this will represent the operation. And the type of expressions that are interesting are either this or this, probably. So we'll have something like A plus B, or probably we'll have something as 1 plus A, and this can be like extended to be 1 plus add of 1. So binary expressions are defined as recursively as, so this can be any type of expression, we don't care, and the operator here will define some of the meta information that we need to parse it. So this will give us 2 things. I will talk about the first one now and the second one later, but this one should give us the actual operation type. And the second part here can be any type of expression. And we'll call any operation of this type that require us to have 2 nodes, two child expression nodes, and the representation of the expression in here, we'll call it a binary expression. And we'll have like other types of expressions, something like not A, or minus A, or plus B, or plus 1. And those are kind of are like prefix operations, because the operator kind of starts before like the identifier or the expression, and they are of the form like operator and expression. So these are kind of prefix operators or prefix operations. So the good way to model this is to model it as a prefix and a binary operation. And for our addition example, we would do like the same thing, but only this time we won't have like a concrete addition node. We'll have like a somewhat of a binary node, and it will contain the actual token to represent what type of binary node is this. So yeah, so what I am going to do actually is remove this. And probably leave it, won't do so much damage, and yeah, and this is still valid. What I will remove is some of the things in here. So we won't be needing something as of the form of an AND expression. We'll have something of a binary expression. And a binary expression should have like another thing, which is like the token. Actually, to only need the token type. Op. And for the literal, we will just return the e.op for now. And those will only be for display purposes. Maybe taking the token is better, so that we can have a visual representation. No, take the literal. Those should be like empty and all right. Bum, bum. Where should I go now? Okay, we should go back to the idea of calling a parse expression. And yeah, so how will we like start parsing? So the idea is try and maybe trying to parse the primary, some kind of primary expression. I doubt that will work. I'm taking a look at the notes I have here, and yeah. One other thing I wanted to mention. So the other thing I wanted to mention is like not all operators are the same. So as you might have noticed in simple math, the evaluating 1, 2 plus times 3 is actually different than evaluating 1 times 2 plus 3, because this actually binds stronger than this. Or the multiplication operator is kind of binds stronger than actually binding the first plus operator. So this will give us a parse tree that is similar than to have 1 and then has an add operation with a multiplication operation that has 2 and 3. And this will give us a 1 which has a multiplication operation with 2, which has an add as a parent with 3. And these AICs are different because like the order of evaluation here matters. And if this got constructed as this, it will give like incorrect results, because when we want to evaluate this, we will evaluate the left part, which is 1, and then evaluating the second part, which is 2 times 3, and then this is like 6, and then it will give us 7. If this, if we evaluate it as 1 add 2 mul 3, this will actually give us like 1 plus 2, 3 times 3, 9. And this is incorrect. So we should take a really good care of having precedence or weight, adding some kind of weight to operators. Yeah, this like this is one thing I wanted to mention because I kind of forgot it. Yeah, so I want to like identify some kind of constants which will represent the precedence kind of our operators. So let's say I have something that's called other, which this will map to anything that I didn't actually define. I'll give it the minimum priority. Let's call it minimum. Minimum. Can't spell. And let's have an add, or okay, so let's do add with a 1, and let's start for and mul equals 2. So those are the basic example. We have add and addition and multiplications, and if it works for both of them, we will extend the example to kind of work for the others. We want to be, well, let's define a utility method. Like get precedence or wait for some kind of token. And I want them to be put in some kind of map. So let's do var precedences for equals map of token type to int, and we want to map plus to add plus but token type lexer dot plus no. Now get precedence would be like precedences dot of token dot type, and we have either we have the value or has. So if it doesn't have the value, we will return I guess the minimum. So we don't know what's this. Otherwise we will return the actual value. Yeah. And multiplication here should have, well, yep, thanks Moad for noticing. I just noticed. No, cool. Another thing that I wanted to note is like I wanted to have mapping functions. So I'm gonna try to implement something that is called a Pratt Parser, and the Pratt Parser actually kind of is actually pretty easy to map a grammar into a Pratt Parser, and the way it works is you identify your lexical rules identified by our grammar, and then you represent them as functions, and you kind of use those functions to kind of parse your actual terms, and that while taking into account the precedence or the weight of each operator. So I will identify, like I said before, like I have two types of nodes. I don't know if I identified the first type. So I don't have the first type in here. So let's do this. Prefix expression. A prefix expression has the operator and has the right part, which is the expression. For this, we will return the op dot literal, and we don't care about anything else. Now, I identify like two types here, or type synonyms. We'll call them like a prefix parsing. Let's call it like a parsing, a binary parse function. And this will map to something that takes an expression and returns an expression. And a prefix parse function. It won't take anything, but will return the actual expression. And functions of this type are going to be used to parse binary operations, such as addition, subtraction, etc. The first parameter is the already parsed left side of the operator, and the function should return the left side. The merged actually should parse the right side and merge both of them and return them as a binary node. Binary expression. Right? Functions of this type are going to be used to parse. I guess they are called unary operations. I'm not sure. Such as negation, minus a, plus 12. The return value is an expression, a prefix expression representing expression. All right, and now we can identify like a bunch of binary parsing functions and a bunch of prefix parsing function. What we know is some parse expression. So I'll just leave here to null. And I want to be able to parse a number literal. And parsing a number literal, if you think about it, it's just a prefix function. So we can do this by, if we suppose that the cursor is actually on the number, the current is the actual number. So we can do like get the current value. So str convert parse int current 10, as I said, 64 this time. Value. If it's not null, we should panic. Good luck, parse integer. Otherwise, should like p.advance and return a number literal expression, where the actual value is the value. So advance and like put this. Yeah, and with some kind of literal. Right? I hope this was like obvious. Now, parsing an expression actually can be tricky. So we have a let's go back here when creating the parser. So the parser should have like a bunch of mappings between each operation or each kind of type of token into some kind of prefix function or a binary function. So let's start with those. So we have a map of token type into a prefix parse function, and we call those prefix funcs, and then binary funcs, and those are binary parse functions. And then those are going to be initialized in here. So we make the prefix funcs equals to a make of this. And we do the same for binary functs. I misspelled binary. And we should make binary parse functions. Now all we have to do is make the p.prefix functions of token type, of a number token type, to be mapped into the parser.parse number literal. Yeah, that's all what is required. And yeah, so whenever we find, and then we have something like, and then we will have a binary function for now, and lexer.plus, whenever we have a plus, we'll see like, hey, try to parse a binary expression. All right. We should probably create this method. And then when parsing the binary expression, we should parse the left side. So we have a current token, right? So we take the prefix function and we say, hey, I have a current token. Give me the function that will allow me to parse the first part, okay? And we say, so I say p.current token dot literal dot type and has, and if not has, the static, no parsing function, no parsing function found for the given the p.current function, current token. Otherwise, we kind of advance, I guess. Let's think about it. So if we can parse the first type, we should, the left side should be like prefix, right? Because we know like calling this function will result in parsing the current expression. And to think of it, I don't need a reference to the current precedence level. So probably all right. So I'll write it otherwise. So I have a func. So I want to have something similar, but this time I want to take some form of precedence. Right? And we want as long we want to advance the current token, and while, or at least for, while the precedence or the current precedence is smaller than get precedence for next type, while we still can, it would be a good idea to think of have a binary functions of the p.next token dot type. So this should get the binary function. And then if it doesn't have a binary function for that operator, we just return left. So we don't really care. Otherwise, the left should be equal to binary of left. And of course, I guess a little of advance. Advance should be called, I guess, here. And then at the end should return advance. Yeah. I guess this should do it. Well, that's the whole gist of it. We'll still like find some bugs, I guess, that we'll need to debug. But so I guess we don't need something like this. We'll need to parse an expression, and this should delegate to parse internal. Let's call mini. And we should have some kind of function that will represent a parsing a binary expression. Expression left. Now, when we are on the left side, on the right side, we should create the binary node here. We should like probably create a binary expression that has left as left and has up as the p.current token. Come on. Binary. Now, we want to parse the right expression. So a good idea to do is like try to parse that recursively, I guess, if that makes sense. So having it as binary, so the right side should be parse internal with get precedence for this current operator, which is like op p.current token. And then binary, that's right, equal right, and we should return binary. So this looks a little bit confusing. Let's back up a little bit. So the first call that we will have is call in a parse expression. And the parse expression should have like an initial precedence, which will give it like a 0 or something like that. And the parse internal will parse the prefix using one of the prefix functions, if it can. And then it will keep advancing as long as its current precedence is smaller than the get precedence, or the next token. And it will keep on construction the tree. And another thing is having a left and a binary here. Calling the binary function here will call eventually to this with this left operand. This will construct the binary expression, create the right with the new precedence of this given operation. So if the first operand was plus, and we had something like 1 plus 2 multiplied by 3, we would expect to parse the first one and go parse the second one as the operand, and then when trying to parse the third, I will try to add 2 with this, and since this binds stronger, we should stop at here, 1 plus, and this will start again to parse 2 times 3, and then make it the right side, the right child. Yeah, I don't know if that makes any sense. I don't know if you guys have any questions, because I'm confusing. I'm confused right now. Not sure if I'm dropping frames or not. Doesn't seem like it. Anybody has questions? No one? Okay, so let's try this with some of our tests. I'm sure there are some tests won't compile, of course, because now, oh, they did. But we are interested in this, right? So let's kind of start from here. On the call to parse, let's start to debug it. So let's start. So we have a parse and calling to parse statement. For now, we default to parse expression. Parse expression with call parse internal with the default precedence and prefix. Now prefix has some kind of has a prefix function. And when parsing the left, the left side is a number literal that has a 1 as a value, and we advance. Now the next token is the end of file. Huh. We shouldn't have an end of file. What's the current token? It's 2. All right, so parsing, I guess we have something in the number literal. We shouldn't be like, I don't think we should be advancing here. But let's remove this. And the current token, I guess, because this will advance eventually. Let's start over. And let's go back to just about here for the first time. Again, this will have, and left now is 1, and the current token is plus. And if now the precedence is smaller and has false because we don't have, the next token is a number. So again, here we should use the current token. So now has is true, and we have a binary function. And now calling the binary function would call parse expression binary. What happened? Actually, don't know parse expression binary. So we got to parse internal, yes. Yeah, and then we got here, and what's the current token? The current token is 2. So we parse it, and the precedence, I guess, is not good. So we will probably just return left, and then we set the right position, and we get back. Right? And this is the first and only statement. Now, the root node has one statement, and the first one has an operand of 2, which is wrong. The actual value is 1, and the right value has an actual value of 2, but the operand is wrong. So we shouldn't. So we have some off by 1 errors. When we create the binary, so this is the current token. I suppose it shouldn't be the current token. It should be I don't even remember what was the actual result. Does anybody remember what was the last value of the operand? We had 2, I guess. So we probably. Anybody remembers? No? So let's try again. So we did that, and then we skipped some things, and we probably, so ended up, so what's the statement? Yeah, operator has like 2, which it shouldn't have. So probably we skip 1. So where's my parse number? That's why my guess is we shouldn't advance at all here. And after parsing, we should like take, right? Should take a look at the next token and then advance. I guess now we'll have a better luck with this. Okay, now it panicked for some reason. So let's see. So I'm going to parse statement, parse expression, parse internal. We try to get the prefix function, and we have the prefix and the precedence for the next token. So my next token is a plus. So next token dot type, and then we advance. Then we call the binary. Right. Huh. For some reason it kind of blows up when you're in the binary. So before, so let us stop it in here in binary expression at the first statement. So at this time, I have the left as 1 and the binary that has a left as 1 and the operand as 1, and the next token, and the current token is plus, and the next token is 2. Okay, so we call parse internal, and we get out of here. Now we go into parse internal. Now the current token is 1, I guess. Yeah, the current token is a plus. So my guess is if I advance here, this should fix the problem. Okay, let me stop. So if I advance there, where's my parser? Advance here. So the current token is, here is a plus, and I want to get the preference of the current token. All right, so let's call it precedence equals gets precedence of p dot current token. Now let's call advance, and let's call it with a precedence. Debugging now, probably. Yep, it kept on looping forever now. That's an interesting thing to debug, and especially on a live stream. Current token. So yeah, I'll jump this. Now what's my current? Is a plus. Now after calling this, my current is 2. We're going to parse internal. We have a prefix function. Yes, we have. So we parse, and we go back with the left, and we have the right. We go back. Now what's the next token? Send a file. We'll go back. We go back. So the token dot type is it's never end of file. Yeah. All right. What did I miss? Okay, I'm going into some kind of infinite recursion. Alright, let's back up. So I have the current token, then we have the current precedence, and then we advance. And in this case, we have a prefix function that we call should we probably stop? I'm not sure. Should we probably stop doing this? We're doing something wrong that keeps on like. So we get the current type, we take the peak precedence, and then we get the peak precedence with the peak token. Something isn't right. Problem is we never advance from parsing an infix expression. So we advance in two parts. So we always, so if I parse this, I advance. I always call advance and then I move in. This is a pickle. So we want to have 1 plus something plus 2. I'm actually pretty lost. Okay, better like see what's going on in here. I'm probably doing something stupid. So I'm ending at the 1. So this is my current. After calling prefix, I'm probably still at 1. And then if the next one has the good precedence, we go and get it with the next token, and then we stop at the current operator. And then we go into parsing the binary. She'll make the left as the left expression and the operation as the current token. The precedence should get it from the current token. And it should advance to the next one. Now we are starting at 2. Hmm. All right, let's see what I have in here. Mm-hmm. This is a pickle, and I can't see what's the problem. So the prefix function can advance. So we parse and stay at it. All right, let's see. Prefix functions. This looks correct. And then we have numbers and plus. Yeah, I don't think we can parse. So this is not valid, I suppose. I'll try the same problem for this. This is a bug. The prefix will parse to the left. The current never. Yeah, my bad. Yeah. Advance. This is my bad. This should solve it. Yep. So this at least doesn't make it like loop on forever. If we have this, yeah, and move to the next one. And it passed, surprisingly. Alright, but I wanted to see. So I want to see like the root node after creation. The root node has one statement. The operator is plus, and it has a left, which is a literal expression, which has 1. And it has a right, it has a literal expression, which is 2, which is good. Now we want to see what's the output. Sorry for that, I actually made a huge mistake about this. So yeah, so let's see what's gonna give for this. Hopefully it won't give something too. Oh, wait a minute. I don't think I have a parser for. It will complain because it can't find the star here. It won't find it. Well, we debug now. And we go to the. Oh, sorry. Let's see how the root node looks like. The root node has 0 statements, and it has an operation with plus, which is a good sign. The left has 1, the right has a multiplication, right, and the actual values too. So it actually like doing the correct thing that we expected it to do, because we have 1, 2, and these should be like in its own in their own like subtree, and then this will contain another subtree, which is good. Now, if we flip this, yeah, so let's try to flip this again. The solvent for this particular issue will, oh yeah, I know it's a null statement, so let's see. The operation is plus, okay, but the left side now has a multiplication in it. Exactly. And the right has 3. Cool. So now we are able to see this. I am gonna delete all the tests because most of them are useless. And we can't be like testing like this. You just use this to kind of bootstrap the project. Yeah, so this is like a math expression. We would like to be able to kind of see how it's gonna be parsed. And let's go back to the parser, and we see like we still have a bunch of operators. A minus, and we have a division, and if I ran the previous tests, it panicked. Why is it panicking? Yeah, because I guess we are missing some stuff. Again, so the root node now has minus, and to the left of it, it has a plus, I guess. Yeah, it's parsing correctly. So now we have a basic support. So let's kind of do a little bit of refactoring for this. So let's wrap this in their functions. So let's do like some register binary func, and then we'll take some kind of function, and then we'll take some kind of token type. I'll take a bunch, I guess. And then for each token type, I want to do p.binary functions of type equals fun. And this is types. I want to have something this. I want to do the same thing here. Register. Prefix file. I'll do the same. And now this will look like p.register prefix functions with x.number. We want this to be as p.parse number literal, and we'll add those later. And we'll do the same here, register binary for p.parse binary. Lexer.plus, lexer.mil, lexer.minus, lexer.div. Yes, I guess. So this should still work after initializing all the functions. Yeah. I guess we're already wasted a lot of time on that debugging bug. I won't be able to do all of the things that I wanted to do today, but I want to add something like to kind of start up what I want to do for the next time, is the ability to kind of see the parse tree, and to see the parse tree, we can either implement kind of string or some string representation for each one of our nodes, or I want to do something a little bit more fancier. So I want to implement something called let's say an node visitor. So just bear with me, because this is the Java geek in me. I'm gonna implement a node visitor, although this is not the Go idioms. None of the Go idioms kind of tells you should write a node visitor, but yeah, that's just the way it is. We'll kind of visit an expression, and visit statement, visit root node, visit binary operation or expression, visit prefix expression, visit number literal, and I want to make all of the nodes accept this visitor as part of their contract. Now each of my so let's start with a number expression, onto your like expression. Visitor dot accept visitor number literal expression. We want to implement the same thing for the binary expression. Same thing for the prefix expression. I guess all of them implements this now. And to kind of test this, we'll have some kind of main file. Public. I will create a new, so the source would be 1 plus 2 times 3, let's say. This is a demo, and then we'll do like a root node equals new parser new with the source dot parse. And then I will do the root node dot accept come to think of it, we never implemented this for the root node. And we accept a printing visitor. And this printing visitor will only like print the node visitor. Okay, so eventually we'll have like something as indent size, and we'll have some kind of buffer. So I wanna like do the whole indentation thing. P dot indent and do buffer dot p dot buffer dot write w. Now for the visit expression, we're gonna like we won't care about them right now because we don't have expressions actually for the current time. And visiting the root node would do like, hey, I'm visiting a root node, so I'll just like do p.buffer, write string, visiting root node. and then we'll do doing the. We should increment the indent by some kind of falsies. Let's do the go away. And then we want the node.statements for each. We want all of them to kind of accept this visitor. And then p.indent with, so that it can like print all of them at the same time. And whenever we are somewhere, we can like do p.print indent. And this pattern will repeat a lot. So in binary expression, we do the same, only in this case, we'll do like visiting left and visiting right. So we do like expression dot left dot accept p, and do the same for right. And for the prefix expression, here we are visiting a binary node. For prefix expression dot we haven't like talked about this yet. And the number literal has no children, and that will just print the indent and then write this visitor number and the expression of actual value. This will give us a decent view of the actual parse tree without using anything else. And nothing happened for some reason. Okay, so let's debug. So going into the accept, so we call visit root node. Oh yeah, of course nothing will happen because I never printed anything. I want to have a string method. p.buffer.string. Right, now should probably see something. Yeah, I never print on the fly, do I? Yeah, I never do. Yeah, so now we can see like we have a binary node, we have a binary expression, and the binary expression has an operator. So let's do like %s to kind of see the actual operator. All right, see now again. Not there. Oh. Letter O. Yeah, so we can see that we have a binary expression which has a plus, and then a number, and then a binary expression which has 2 times 3. And if we do like something that is more complex, this will help us like along the way to debug in case of we have problems. So we have a root node, we have a binary expression, which is like this, and we have the left side contains a plus binary expression that has 3 to one side and 2 to the other, and then we have 2 in this side. You can see like it parses correctly. So yeah, I guess that's pretty much it for today. I guess we reached the 6 hours mark, the 2 hours mark. I'm feeling a little bit tired. Maybe next time we continue like with the testing part. How can we test ASTs better? And we'll dive into parsing more statements and probably more expressions, but at least now we have the groundwork for the parser thing. So if you guys don't have any questions, we'll call it a day. If you have ideas or something that you want to implement in the language, or that you think you can improve, please send me a pull request on the GitHub repo. I'll be happy to review it and submit and pull it in. And if it's like if you guys like are highly motivated, we can have like live streams with people actually joining in and like discussing PRs at a later point of the video. Yeah, looking forward to it too. Thanks, Matt. So, no more questions. Cool then. I guess that's it then. See you guys on the next stream. Bye bye.